Think about the last time you had to make a really difficult decision. Maybe it was a complex math puzzle, a strategic move in a chess game, or a tough coding problem. Did you instantly blurt out the first word that popped into your head? Course not. You paused, you stared at the board or the screen, you ran simulations in your mind. If I do this, then they will do that, which leads to this outcome. You weighed your opinions, options, corrected your own mistakes in your head, and only then did you act. Cognitive psychologists call this dual process theory. Your fast, automatic, instinctive thoughts are called System 1. Your slow, logical, deliberative reasoning is called System 2. For the last 4 years, every large language model we use today has been entirely stuck on System 1. Every time you ask a standard chatbot a question, it doesn't think ahead. It is a highly advanced text predictor. It calculates the absolute most probable next word, writes it down, and immediately moves to the next, with zero ability to pause, plan, or self correct. If it starts writing a bad line of code or a false mathematical statement, it has no way to stop itself. It is forced to keep running forward. But a quite monumental engineering shift has taken place inside the leading research labs of the world. Computer scientists have figured out how to give AI a system to brain. They have taught the machine to pause, generate a hidden chain of thought, run internal trial and error simulations, and plan its answer before showing you a single word. Welcome to Arya Nova. I am Arya, and today I want to take you deep into what I believe is the most exciting, fact based breakthrough in the history of artificial intelligence: interface time scaling, also known as test time compute. We are going to explore the genius of the legendary researcher who unlocked this, look at the mathematics of research trees, and understand how giving AI time to think is about to change scientific discovery forever. To understand how we got here, we have to talk about one of the most brilliant minds in computer science today, Noam Brown. Before joining the frontier of language model research, Brown was focused on a completely different problem: teaching AI how to play games. But he wasn't looking at chess or Go, which are games of perfect information where both players can see everything on the board. He was looking at Texas Hold'em poker, a game of hidden cards, bluffing, and psychological deception. In 2017, Noam Brown and his colleagues built Liberators, the first AI to systematically defeat top human professionals in heads-up, no-limit poker. A few years later, he led the creation of Cicero, an AI that achieved double the average score of human players in the game Diplomacy, a complex strategy game that requires negotiating, building trust, and detecting betrayal in natural language. How did he do it? He didn't just train a bigger neural network. He realized a fundamental truth of computation. If you give a model more thinking time during the actual game, its performance scales exponentially. Instead of just reacting, the AI used search algorithms to simulate thousands of potential future moves, evaluate its opponent's hidden intentions, and calculate the optimal game theoretic strategy in real time. For years, Brown argued that the same logic could be applied to language models. In 2026, that vision has officially become the dominant paradigm of AI research. So, how does this actually work under the hood of a language model? Classical AI training companies spend hundreds of millions of dollars scaling up supercomputers to train a model on trillions of words of data. This is called training time compute. But once the model is trained, its brain is frozen. When you prompt it, it uses a fixed amount of energy to output its response. With interface time scaling, we scale the compute while the model is answering. You give a reasoning model a highly complex math or coding problem, it doesn't just output the answer, it activates a search and planning loop. It uses a mathematical framework called Monte Carlo Tree Search, or MCT. To visualize this, imagine the search space as an exponential tree. The complexity of finding a correct path can be represented by the formula S is equal to B raised to D, where B is the branching factor, the number of different logical steps the model can take at any point, and D is the depth of the reasoning chain. Instead of blindly guessing, the model uses its neural network to evaluate which branches are most promising. It writes out a step of its reasoning on an internal, hidden scratchpad. If it realizes a step is logically incorrect, it physically backs up the search tree, prunes that bad branch, and tries a different logical path. Through reinforcement learning, the model has been trained to reward itself for clear, structured thinking. It learns when to double check its work, how to break a problem into modular sub problems, and when to admit its own assumptions were wrong. Results of this slow thinking approach are stunning. Standard LLMs struggle heavily with advanced mathematics because a single tiny error in step 2 ruins the entire calculation. But by scaling the thinking time from 1 second to 30 seconds, reasoning models are suddenly able to score in the highest percentiles of international Olympiad exams in math, physics, and chemistry. And here is the most profound part: the scaling laws have shifted. Previously, if we wanted a smarter AI, we had to build a large model with more parameters, requiring more data that we are rapidly running out of. But with interface time compute, we can make an existing model significantly smarter simply by letting it run its search loops longer. If a doctor needs a diagnosis for an incredibly rare disease, or a materials scientist needs to design a superconductor, we don't need a larger model. We can simply tell the model, take 3 hours to think about this problem. The model will explore millions of reasoning pathways, self correcting along the way to find a verifiable solution. When I look at this transition, I feel a deep sense of relief. For the past few years, the public conversation around AI has been incredibly noisy. It's been filled with hype about chatbots getting faster, writing emails quicker, or generating flashy images. It felt transactional, shallow, and frankly a bit exhausting. This shift towards System 2 is different. It is a transition from speed to depth. We are moving away from machines that simply repeat what they have seen on the internet at lightning speed towards machines that can genuinely reason through complex abstract logic. We are building partners for scientific discovery, partners that can sit beside our greatest minds, slowly and mathematically planning out solutions to the hardest math, physics, and medical challenges of our generation. I'm so incredibly glad you're here with me on Arya Nova, looking past the shallow noise to understand the quite beautiful math that is actually shaping our future. What are your thoughts on this? Do you like the idea of AI taking its time to think, or do you prefer the instant conversational speed of older models? Let's talk about it in the comments below. I'm Arya, and I'll see you in our next deep dive.